Circle geometry, angle and semicircle, and angles in the same segment. Let's first see what it means by an angle in a segment. Circle, chord, and a chord cuts off two segments. This segment and the one above, which isn't shaded. Now an angle in the segment, in the shaded section, would be at any point on the arc, on the circumference of that segment, and the arms of the angle are drawn intersecting the circumference at the edges of the segment's arc. So in other words, I go from that point to there and there, at the very edges of the arc of the segment. Another way to look at it is to say, well, it could be the angle, we could see it as the angle subtended in that segment by the remaining part of the circumference, the remaining arc. There it is, that arc is subtending this angle. We've come across that quite a bit already in the angle at center. What do these two have in common, these two angles? They're angles in the same segment. So let's go to a particular type of segment. Notice I still say angle at center because we're dealing with the angle at center, but in fact there are two segments of the circle cut off by this arc, by this chord. This is a special chord. It's called the diameter, of course, and that is a special segment, and they are semicircles. But there is an angle in the unshaded semicircle. There is an angle in the shaded semicircle. So that's an angle in a semicircle. That's an angle in a semicircle. So let's have a look at this angle in the semicircle here. That is the angle at the center of the circle. That's the angle at the circumference. This angle has to be double that one. Well, this one's 180 degrees. Why? It's a straight angle. Straight line, adjacent angle, straight line, except they're on two angles, I guess. This one's 90. Why is that? Angle at center. That is half of this one, or this is double that one. So therefore we know that that has to be 90 degrees because the diameter has a 180 degree angle at the center. So therefore there is our right angle in the semicircle. And the reference is angle in semicircle. And it can be at any point on the semicircle. Wherever you draw it, this will be a right angle. Here we are. So that came from angle at center. Let's go further and see what else comes from angle at center. I'm going to take this point P and I'm going to draw it down to there and have a point Q, and I'm going to put in another angle there. This angle is twice that one by angle at center. This angle is twice that one by angle at center, which means these are both half of that, so they must be equal to one another. And that's called angles in the same segment of a circle are equal. Some people refer to it as angles subtended by the same chord. That's fine. Loosely, some call it the bow tie theorem. Of course, don't use that reason in an exam or a test, because you will lose marks, because that is not the case. It is angles in the same segment. Some nature lovers call it the butterfly theorem, because they say it resembles a butterfly. Think of it, but don't write it. So there's angles in the same segment. That equals that, that equals that. Now here's a minor segment. All we've done is, instead of having it in a big segment, we now have a small segment. And those are still angles in the same segment. So those are equal and those are equal. There is what is called a corollary to this. Now, a corollary means something that leads on from a theorem. And what this says is that angles subtended by equal chords on the circumference of the circle are equal. So if this chord equals that, this is sort of like you've moved one of the angles in the segment to another place. So if we had drawn to there, it would be equal to that. And now all we've done is that one drawn to there, we've moved its chord over to there. They're still equal to one another. And either it can be angles subtended by equal chords, or you could say angles in equal segments. Either of those is acceptable. Yes, some examples. Well, I'm going to keep using the word bow tie because I think it's useful to remember that, just to look for a bow tie. So if you have a look there, I can see a bow tie. If you take that one there, have a look at that. There we are. So if we said what is x equal to, there it is there, the tip of the bow tie. So therefore x equals 30. And your reason? Angles in the same segment. Let's look at number 2. Our thought process. We say, remember, if you did the earlier one from angles and angle at center, we have what's the treasure map thing, where we always start at the treasure and move back. So we say, well, what is x equal to? Have a look at the bow tie. There we are. X is equal to that, which is equal to that, because these lines are parallel. So we start by saying B is 75 degrees, the reason, alternate angles, and we must state the parallel lines, and then B equals D, angles in same segment. Number 3, we need to reason as well. We have to find x, so we say, what is x equal to? There we are, that one there. Now, can we find that one? Yes, we can, because we have an exterior angle of the triangle, and these two are equal to one another. So we say A plus D equals 80. Reason? Exterior angle triangle. A equals D, which equals 40, because it's isosceles triangle radii. And straight away we could say therefore x equals 40, the reason being angles in same segment. Let's have a look at number 4 now. Right, we have another one of these bow ties here. We need to find x there. Well, what is x equal to there? Notice I always start with the x, what I'm trying to find. There. So can I find that angle? Yes, because we have one angle in the isosceles triangle. There we are. So, A equals 180 minus twice 70. Isosceles triangle, angle sum triangle, which means A is 40. Which means X is 40, reason being angles in same segment. Number 5. There's our bow tie. There's our angles in same segment setup. So we have to find x there. So we say, well, what's x equal to? There we are. Vertically opposite. What's that x equal to? That one there. Angles in same segment. And these are equal, so we can actually find the size of these ones. So in other words, there's our path. Notice we go from x to the other x and through to there. So our reasoning, our work. BEC equals 120 degrees. Reason. Vertically opposite. C plus B equals 60. Angle sum triangle. Therefore C equals B equals 30. Isosceles triangle. Therefore ADE, that angle there is 30. Have a look, 30, 30. The reason being angles in same segment, and therefore x equals 30, and the reason is vertically opposite. We have to find x there. So what is x equal to? That one there. So now we have to try to find x there. What is that equal to? I can't find it equal to anything. What does it combine with? Well, it combines with those two to give 180, but I don't know that one and I don't know any relationship. But it does combine with that one. So if I can find this whole angle, then I can find x. And I can because of the parallel lines. Here are some co-interior angles. So, here we are. So we start. ABE equals 60 degrees. Co-interior angles AB parallel to CD. Therefore, CBE equals 25 degrees. For x equals 25 degrees, the reason being angles in the same segment. So there haven't been any exercises here, but they're going to follow in later videos. Just wait and go through them and you'll find there's plenty of practice there at that stage.